In previous videos, we went in depth on looking at sine and cosine periodic functions. In this video, we will look at their reciprocal functions, cosecant and secant, and we're also going to introduce tangent and its reciprocal, cotangent. In the previous videos, I went in depth into topics such as adjustments to the period, amplitude, vertical shifting, and horizontal shifting, also known as the phase shift. We will be doing the same in this video series, but we will probably not go as in-depth as I did in those previous videos. So if you have not watched all of the sine and cosine videos, please go back and watch those. So let's start off with talking about sine, cosine, and tangent in terms of our good friend, our mnemonic device, SOHCAHTOA. So the sine is going to be the opposite over hypotenuse relationship on a right triangle. There's the SOH, S-O-H. Cosine is adjacent over hypotenuse. There's the CA of SOHCAHTOA, C-A-H. And then tangent is opposite over adjacent. And this would obviously be looking at some angle theta, or T as written in some of the books, to the sides and their relationships from angle theta. Now the cosecant is going to be the reciprocal of sine. Reciprocal means, in layman's terms, to flip on its head, or in more mathematical terms, the reciprocal is defined as 1 over x from its parent function x. So we have hypotenuse over opposite, that is the reciprocal of opposite over hypotenuse. Secant is hypotenuse over adjacent, and cotangent is adjacent over opposite. This is probably why we don't have another cool mnemonic device for the reciprocal functions, because once you have SOHCAHTOA, you can easily derive the reciprocal functions. Now let's look at a unit circle. In the unit circle, the hypotenuse is going to be equal to 1. And from that theta, the opposite side is going to be the distance y, because from theta, the opposite side is y. And so therefore, in our unit circle of x, y, and 1, sine is y. Cosine is x, because that would be adjacent over hypotenuse, and tangent is opposite over adjacent, by definition. Now, cosecant is going to be the reciprocal of this. So this is going to be 1 over y. And the secant is going to be the reciprocal of this, which is 1 over x. And as we're going to see, the reciprocal of tangent is cotangent, as x over y. Now I find it's very good to derive our secant and cosecant in the example underneath this one from their parent functions, cosine and sine, respectively. So let's kind of think to ourselves here, what does it mean to be reciprocal? Well, it means that at this value, we're going to take its reciprocal. And its reciprocal at 1 is going to be 1. Now, at this point, at pi over 2, we're going to take the reciprocal of 0. Now, here's the thing. The reciprocal of 0, which is normally 0 divided by 1, is now 1 divided by 0. And 1 divided by 0 is a problem, because 1 divided by 0 is an undefined point. So that means this solid line that I drew is now an asymptote line. And an asymptote line is a line in mathematics that we cannot cross. What's important about this asymptote line is usually if you were drawing it, you probably should try to draw it as a dashed or light line. But I've found that using this program, if I do so very lightly, it's going to not come out very well. So we're going to look at negative 1. The reciprocal of negative 1 is negative 1. And here's another place at 0, at 3 pi over 2. And this is going to be another asymptote line because the reciprocal at 0 is going to be undefined. The reciprocal of 0 is undefined because it's 1 divided by 0. So in fact, all of these places where our original cosine line crosses the x-axis, these are going to be asymptote lines. The reciprocal at 1 is 1, and the reciprocal at -1 is 1, and so far 1 is 1. So what we have to do is we have to think like, okay, so if this value here is 1/2, so I should probably take the reciprocal of that. So think about the height at 1/2 here, okay? So here's the height at 1/2, so then this would probably be like 2. So here is the reciprocal line in blue. You know, let me change that to a different color. That might show up a little nicer if I just made it green here. Okay, so you see this at -1 right there. So this is about -1/2. The reciprocal of -1/2 is like -2. So here's this spot, and that spot would be mirrored on the other side. So from the vertex of my original cosine function, you may have heard the word vertex in your college algebra class, from the vertex we're going to create these reciprocal waves that move in this direction, kind of like, if you want to think of it, the opposite direction here, or I should have said the reciprocal direction. But again, things get, your brain probably knows what to do here because it just moves in this different way. So you got to be very careful when making your cosecant and secant waves, because you're going to first of all probably want to fill in the asymptote lines first, which I will do now. Again, if you're doing this, you probably want to use a dotted line or a light line. I'm just choosing red just so they stand out. What's important about these red lines is you need to know how to write them. Now you might say, what do you mean? I'm just, making a vertical line, and I understand that, but you need to also know that this is an actual function. The asymptote line is the function x equals pi over 2. Just as the midline was a y equals equation for a horizontal line, this is a vertical line, x equals, and all vertical lines have an x equal equation to it. This is x equals 3 pi over 2. Oh, don't fail me now. This is x equals 5 pi over 2. And this is x equals 7 pi over 2. Okay, so what I'm going to do here is I'm going to create with my green pen again that beautiful secant wave. Here's my secant wave. You'll notice that I don't need to draw the cosine wave. I can just see the pattern turns around at 1 and -1, and that's half smile, frown, smile, frown has to end with a half smile. As a requirement of your test, you're going to have to show 2 full periods of a secant wave, and without drawing this little half smile over here, you're not actually drawing 2 full periods. You're drawing 1 3/4. So now we have our secant wave. Let's focus on that green and red side and talk about the domain and range. Now let's first give the I'd want to do set notation first, and this is the reason why I want to do set notation is because you're going to see why set notation for problems that have these inconsistencies, these little gaps, you're going to see that set notation is going to be your best friend. So let's talk about the domain. These are x values. So we're going to have our little set symbol, x knocking on the door, which is x belonging to the group where x can be anything but these red lines. So x cannot be 1 pi over 2. Okay, the reason for me saying 1 is very important here. So 1 pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. Now you saw me name each number in front of those pi's, 1, 3, 5, 7. Does that sound, I don't know, does that sound somewhat like a pattern to you? 1, 3, 5, 7? I think it does. Those sound like odd numbers. But more than just odd numbers, they're odd integers. So what I'm going to do is I'm going to write that k is not or x is not equal to k pi over 2, where k, this number in front of pi, is going to be an odd integer. Now, I might get a little sloppy as I go through these because I'm going to kind of assume if you say the word odd, you're talking about an integer. An integer is a positive negative whole number. An integer is not an irrational or rational number. And I think it would be hard to think of what is an odd rational number? Like, what's an odd fraction? Does the numerator and denominator both have to be odd, or can one of them be odd? Is 2/3 odd, even though, because of its denominator? Again, we just don't want to split hairs this much at this level. So let's just say that k is odd. K is odd. And that kind of helps a little bit. Now, if I was to do interval notation here, I would need, the space between these two. So I would need between, pi over 2 comma 3 pi over 2. And then what I would need is I would need to connect that with 3 pi over 2 and then go to the next one, which is 5 pi over 2. And then I need to go to the next one, which was then 5 pi over 2. Okay, now at this moment, I'm kind of thinking like, wait, wouldn't I be doing this forever and ever in both directions? And I would. So this is why I don't like interval notation for my basic secant function, because my interval notation couldn't do this very easily. So let's now talk about the set notation for the basic secant function. The set notation is going to be y knocking on the door, or y belongs to all these values, and let me get a highlighter here to show you. It looks like my y values will exist up here. See how my green arrow kind of creates these y values? And then look, they kind of exist here. But there's this giant no man's land between -1 and 1. And so the way I like to write that is I like to write that as two separate things. I'd like to say that y can be less than or equal to -1. So you'll notice that if I make a horizontal line right at that yellow space, I could be below that horizontal line at -1. And I'm going to put a word or, because I can have this situation as well. Y can be greater than or equal to 1. So this is fine. And this is actually okay to write in interval notation, whereas the interval notation for the domain was a cluster. Let us look at how we would write the interval notation here for the range. That would go from -infinity to -1, and we're going to put a nice hard bracket on it. And then we're going to put a union symbol here, because what we want is we want this, and we also want -1 to, or not with -1, we want +1. Get rid of that. +1 to infinity. So this is the proper interval notation for the basic secant function. Now what we're going to do in the next part of this video is we are going to derive the cosecant from the sine wave. Now this is going to go a little faster because we actually have kind of the pattern now established of how we're going to use the parent function, in this case sine, and we're going to now derive cosecant. So the first thing we should do is create asymptote lines wherever the parent function, in this case sine, crosses the x-axis at 0. And the reason why we're making asymptote lines at these marks is because here we have undefined functions, because 1/0 is undefined. So here are my 5 asymptote lines. Starting off at 0, and then this would happen to be 2 pi in the middle, showing 1 period of sine, and then 4 pi at the end. Our gap is pi over 2. These gaps and periods are going to be very important as we go on in this unit. So let me change to green and do my inverses. And again, like before, the vertex of 1 is our middle point here for this little smile. And if we go, to this half distance here, the reciprocal of half is 2. So we're going to make these smiles and frowns over and over again. And a lot of students really like cosecant because it starts and ends so evenly, unlike the secant that you saw before. Cosecant has the asymptote lines at 0, pi, 2 pi, 3 pi, 4 pi. So let's write down all those asymptote lines in red. And again, if you are doing this, you're probably using a lighter stroke, or you are using a dotted line. All right. I find that if I put a ton of dotted lines on this paper, which is this virtual Microsoft paper, it will start to glitch on me. Okay, so now in green, I can make my smiley faces and frowny faces. I'm not trying to be like super accurate like a computer would be. I'm literally getting the points on the paper here, and I should label my asymptote lines. This is x equals 0, x equals pi, x equals 2 pi, x equals 3 pi, and then x equals 4 pi. Because my gap is pi over 2. So let's talk about the domain. Now we're not going to do the interval notation, but let's look at our domain. Really, x can be anything as long as it's not an asymptote line. And here's 0, 1 pi, 2 pi, 3 pi, 4 pi. So from 0 pi to 4 pi, now you see what I did there? I said 0 pi. So I must then basically say that x just cannot be anything that's k pi as long as k is an integer, positive or negative whole number, and I should include 0 in there too. Positive or negative and including 0. All right. So we're going to say k is an integer. Now the word integer is spelled this way. I-N-T-E-G-E-R. K is, I should have put an in there. K is an integer. But that gives us the right answer here. So k is an integer. I'm going to show you in the next video a shortcut for writing all of these words out. Okay, so we're not going to try the interval notation, because the interval notation, again, is not going to give us anything that's, it's going to give us an infinitely long series. So, and I feel like at this level, this is as much as we really could do or need to do. Let's do the basic cosecant range. So y, again, is going to be less than or equal to -1, or y is greater than or equal to 1. Now, we can do this in interval notation as well. We can go -infinity to -1 with a bracket, because we can actually connect to these -1 dots here. And then we actually want a union symbol, and we want to then go from 1 to infinity and make sure we have the 1 with a bracket, because we can actually connect to the 1. And we want a parenthesis at the infinity mark, because we can go there. So this derives cosecant, and it also we have derived previously sine. So please stay tuned to the next video, where we're going to talk about tangent, cotangent, and how the domain and range of tangent and cotangent can be written. Also, we're going to talk about how tangent and cotangent are different in terms of their period and in terms of their gappage as we draw them in our periodic functions.